What is conventional press and sinter powder metallurgy? Conventional press and sinter technology uses metal powder molded by compaction in a closed die. Molded three-dimensional green compacts are sintered and finished to produce a variety of parts used by automotive, lawn and garden, recreation, hydraulics, and agricultural markets. When designing powder metal components, it's often asked, what are the size limitations? The size limitations are dictated by the equipment more than geometry. However, there is a very important concept at work here, and it's called aspect ratio. And if you look at this graphic, we see in the bottom left a 1-to-1 aspect ratio. That is a 1-inch diameter by 1-inch tall component. If we apply 35 tons per square inch to a typical iron powder, we'll achieve around a 6.95 gram per cubic centimeter density. If we take the same 1-inch diameter and make that 6 inches tall, we have a 6-to-1 aspect ratio. If we apply 35 tons per square inch to that component, we can achieve a 6.7 grams per cubic centimeter density. And what we end up with is a density divide or density split called a neutral axis, approximately right in the middle of that column. And this assumes that we compact this from both ends. That neutral axis is important to understand because it is in fact lower density than the ends of the component. If we go to the middle example, we see an aspect ratio of approximately 12-to-1. At a 12-to-1 aspect ratio, the neutral axis can be very pronounced. And since density is so important to the mechanical properties of powder metallurgy, if you design a part that has a very, very high aspect ratio, either in itself or in some of the walls, i.e. the skirt or flange of a component in the direction of pressing, you'll get a wide variation in properties in that component. And it's not a problem to make it if you understand the implications. So it's important that we understand this concept of aspect ratio. When we look at the basic conventional PM process, we start with metal powders. Those metal powders are blended or mixed together with lubricants and other alloying ingredients. From there, the press-ready mix goes to the compacting process, where the powder is consolidated in a closed die and formed to the prescribed density. After compacting, the components are then transported through the sintering furnace, where strong metallurgical bonds are formed between the powder particles. And in many cases, parts are finished and ready for consumption, shipped to the customer at this point in the process. Most of the powder that's used in the conventional powder metallurgy industry is produced from water-atomized material, where high-quality metals are melted and then poured through a tundish and hit with high-pressure water and atomized. This graphic shows the flow of water atomization. We start with high-quality scrap iron in this case. The iron is melted and then poured into a ladle, and from the ladle it's poured into a tundish. Through the tundish, the material then flows into the atomization area, where high-pressure water converts the molten metal into a powdered material. After the material is atomized, it goes through a dewatering process, and then the black powder is stored in bins. From those bins, the material goes into the annealing furnace, where it is annealed in a protective atmosphere to remove the oxidation that's introduced during the water atomization process. After annealing, the powder cakes are then pulverized and crushed and subsequently screened and packed out ready for shipment. Powder is prepared for production through a process of blending and mixing. Elemental or partially alloyed or pre-alloyed metal powders are mixed with lubricants and other alloying materials such as copper, nickel, graphites, and lubricants for compacting. In the blending process is a thorough intermingling of powders of the same nominal composition, such as two different types of iron powder. Mixing is the thorough intermingling of powders of two or more materials, such as iron and copper or iron and nickel. After mixing, the powder is then brought to the compacting press. I'm going to talk about how mechanical properties are developed in powder metallurgy. And number one is the number, size, and shape of the voids, or the density. The density of a part is the weight per unit volume. And density largely determines a lot about the properties of a powder metal component. Here you can see the compacting process, where the powder is carried over the die cavity with the feed shoe. The upper punch then closes off the die and molds or forms the component in the closed die. In this case, we have an upper punch, which is now entering. We have the lower punch, which is stationary, and the die in red, which is movable. The upper punch closes off the die after filling the cavity. The lower punch remains stationary. The die travels down. This process is known as withdrawal type compaction, and you can see the green component that's formed. Compaction establishes the density of the powder metal compact. In this graphic, you can see a powder particle, and you can see the deformation that occurs in compaction. So what's really happening in the compacting process? As we increase density, we're decreasing porosity. And what we see here is an increasing in the area of contact between powder particles due to particle deformation in compaction. In this graphic, we see the part was pressed to a fairly low density of 6.7 grams per cubic centimeter density, and we increased that density to approximately 7.0, and to the far right, we have increased the density to 7.2 grams per cc. And what you can see in the yellow oval is the fracture surface. This is where the powder particles were in contact with each other. And we are looking at the area of contact between powder particles that has been sintered together. The fracture surface that we're looking at represents that area of contact. And you can see as the density increases, we can see the increasing area of contact. And this is the effect of density on the mechanical properties in powder metallurgy. So the second part of the mechanical properties triangle is developed in the sintering process. So after parts are compacted, they're taken to the sintering process and put into the loading zone of the furnace. This is a continuous mesh belt sintering furnace, and the lubricant that was used to facilitate compaction will be removed in the delube zone at approximately 1350 degrees F in a protective atmosphere. After the delubing, the parts enter the high heat zone where they're sintered at 2050 to 2100 degrees F. Sintering is the formation of strong metallurgical bonds between the powder particles that have been consolidated in compaction. Then we go through a transition zone where the sintered compact is stabilized, and then into a cooling zone. After the parts exit the cooling zone, they come to an unloading area, and the parts are then unloaded and staged for the next step in the PM process. During the sintering, we see the particle-to-particle welding, or the sinter necks that are formed. This is where we're actually welding those powder particles together. Here you can see the effect of density on mechanical properties. Across the bottom we see density, and on the Y scale we see tensile strength. And you can see the lockstep agreement between density and tensile strength. In some cases, we require very high strength components and or parts with very good wear properties. So we increase strength and improve wear by going through a quench and temper process. The tempered martensite is a result. Here we see the low carbon condition of iron called ferrite in the microstructure. In the middle slide, we see the addition of carbon or graphite, combined carbon, to produce a pearlitic or pearlite microstructure. And in the far right, we see a martensitic high carbon form of iron. And you can see under each slide is the yield strength. The ferrite is 29,000 psi yield strength, approximately. The pearlite produces approximately 53,000 psi yield strength. and the martensitic microstructure produces 85,000 psi yield strength. These materials are all processed at the same density, but just produce different microstructures. And you can see how the properties improve. Compaction develops the area of the particle-to-particle bond. Sintering welds the powder particles together, and the alloy composition and heat treatment determine the strength of the particles. Let's take a look at some PM applications. Here we have a notch and pocket plate that are used in one-way clutches in automotive transmissions. They're made from sinter-hardened steel and iron carbon steel. Here we have an automotive planetary carrier system, and you see a number of PM components here. They're pressed and sintered and then sinter brazed to form the carriers, and the gears are powder metal forged material. Here we see stator cores for electric motors made from soft magnetic composite insulated iron particles. The rotor core for a hybrid electric motor is made from sintered soft magnetic outer rim and sinter bonded to a copper steel inner hub. Powder metallurgy is a global commercial business and highly studied science. Conventional PM offers cost-effective solutions for high-tolerance applications. If you want to learn more about powder metallurgy, visit picpm.com.